What can I say? It's an honor to have Jonathan Stallrich in ASQ El Paso, okay, as a speaker. He's an excellent statistician. No, he's not only good, he's excellent, okay? So John Stallrich is an associate professor and director of the PhD program for the Department of Statistics at North Carolina State University. He earned his PhD in statistics from Virginia Tech in 2014. His research interests include design and analysis of screening experiments, computer experiments, online control experiments, and functional data analysis and variable selection. Okay, so as I was telling to the group, Jonathan contributed to presentations in the 67th annual Fall Technical Conference in Houston, Texas, in October 7 to 9. Okay, so it was absolutely great. Okay, I attended to those. Okay, and I can testify that Jonathan is an excellent statistician. Even though I teach in my days in master level, but there's no way, Jonathan is in another level, really. That's why I said that he should consider one of the best statisticians in the country and in the world, okay? So let's pay attention very closely to him because he's high-level statistics, okay? So welcome.
Well, thank you very much for that kind introduction. As I said earlier, I hope you're not overselling me a bit, but I'll do the best that I can. So let me go ahead and share my screen. Let's see, I'm going to minimize this. So I can't see you all, so if you have a question while I'm giving a presentation, you'll need to speak up. Otherwise, I'll look at the chat after I'm done. And what I'm hoping is I can go through this presentation and then have some time for demoing some of the R code that accompanies this paper. Just to give it a quick shout out, if you Google the title of this paper, you'll see a couple links that pop up. I would recommend that you access the paper through the Journal of Quality Technology website. It is open access. You don't need to have a paid subscription or anything like that for it. You should be able to click on that link and download it, the paper automatically.
Okay.
And there should also be supplementary materials for like my my R code and things like that. So just wanted to give a shout out for that in case you don't follow everything in this talk. So the title of my talk is Powerful Foldover Designs. It is a talk aimed at people that are familiar with doing a screening design. I will give a quick background about these types of designs and an example of how they're used. But these designs have been studied for a long time, since the 1950s and even earlier with that. And what's surprising is that there are still new things that we're discovering about these designs, even though they've been studied for decades. So just a quick introduction about what a screening experiment is. These are very common in a lot of areas, particularly engineering. The idea is that you have multiple factors that you can manipulate, let's say M factors. And the point is that, you're trying to, let's say you're trying to optimize some response. Maybe you're trying to optimize some manufacturing process. And the idea is that if I change these factors, I'm going to change the response. And you want to find out, you don't think that all of these factors are equally going to contribute to changing the response of interest. You want to find out which ones are really the most important and then optimize along that subset. So the goal of the screening experiment is to find which of this subset of M factors is actually the most important. To make the discussion easier, let's just say that we standardize all of the sort of numeric factors that we have to be between plus or minus 1. That's a pretty simple transformation. And let's say if you have a categorical factor, let's just focus on the case where we have two different settings for that categorical factor so that we can code it as like a plus or minus 1. So when you talk about an experimental design for a screening experiment, you can represent it as this matrix D, where each row of this matrix is describing the settings for the m different factors. And so you can write down this the matrix to look like this, kind of like a table that you would have. So while I was developing this work, I actually had someone from the biomolecular and chemical engineering department reach out to me, a grad student, a fantastic grad student, actually, who had done a lot of research on his own. And he said, okay, well, I've kind of have an idea of what I could do, but I wanted to reach out to an expert. The idea is that I'm trying to optimize across 8 different factors for making ethylene from ethane. It's a little bit more complicated than that, but for the purposes of this talk, that's all we really need to care about. And they said, well, I've got 8 factors. Technically, they're all numeric, but I don't really care about the extreme settings. So all of the design matrix has either a plus or minus 1 in it. And so if you think about all the possible rows that you could have for this design, that's 2 to the 8, which is 256 possible rows. So if I wanted to do every single combination, I'd have to run this process 256 times. It takes 2 months for them to do 20 runs. So that wasn't going to be feasible for them to do that. But they still wanted to be able to find something out of this. So we want to choose our design that optimizes this analysis, this screening performance. So for us to know how to do that, we have to know how we actually plan on analyzing the experiment. And this is exactly how I like to describe the way people should be thinking about experimental design is you're kind of going into this before you collected any data. You say, I plan on roughly doing this. I can afford to do this many runs, and I'm going to analyze my data in this way. How can I find the best design that optimizes this analysis? So you have to have a lot of knowledge on how the analysis is done before you can collect the data. So the way people commonly do this is they make sure that when they pick the settings of their factors, they do it in such a way that they feel pretty confident that the settings of the factors, these DIJs, that you can argue that these factors affect the response with some sort of quadratic polynomial. So you'll have an intercept term, you'll have linear effects, that's what these are. You'll have bilinear interactions, and then you'll have quadratic effects for the individual factors. But it's not going to fit it perfectly, so you add some error term there, EIJ, which you usually assume is normal 0 sigma squared. But even this can mean that there's a lot of things that you need to estimate. This is a regression model. There's parameters that we need to estimate. How many are there? Well, there's going to be up to, if you fit this quadratic model, 1 plus 2 times m plus m choose 2 coefficients, which is still quite a bit. So for example, with this ethylene experiment, if I ignore the quadratic effects, I still have, just doing some quick math, 37 possible effects that I would potentially need to estimate. And I'm saying I want to do that in 20 runs. Well, it's not possible to do that using regression methods because you need your run size n to be at least as big or bigger than the number of effects that you want to look at. So we have to do some sort of other analysis strategy. And so here's what's commonly done is you take this model and you partition it into 2 different pieces. This part anyway, not the error part. So you break it up into 2 different pieces, and I'm writing these things in matrix form. And we do this because there's a lot of empirical evidence to suggest that, yes, there's a lot of possible effects I could estimate, but for a lot of practical problems, there are these simplifying relationships that really we can go in and assume that they're true from the very beginning. So we call these the effect principles. The first one I'll talk about is effect hierarchy, which is saying that the magnitude of the coefficients in this beta 1 vector tend to be larger than the magnitude of these second order terms here that include the bilinear interactions and the quadratic effects. What that means is what's mostly important about this model, what's really driving a lot of the variation of this model are these linear main effects. So I want to make sure that I estimate those things as well as I possibly can. And then if I have anything left over, then I can look at the second order effects. The second principle is called effect sparsity, which is saying that a lot of these betas are actually going to be basically 0 and that they could be dropped from the model. Now, that's really important when it comes to our problem because we're saying that I have possibly more effects to estimate than the runs. But if I can assume that a lot of these effects are actually not really important, that gives us some hope that we'll be able to still find the effects that are really important. And then the last one, which is always really confusing, is called effect heredity. And basically what it's saying is that you could think of these second order effects as being children of these first order effects, meaning that these children can't exist unless their parents exist. So for example, like the bilinear interaction between factors 1 and 2, that can't be in the model if unless both factors 1 and 2 have important main effects. So that's kind of like this genetic interpretation. There's different levels of heredity. Sometimes people say, well, I just need one of the parents to be there. It's kind of weird, but that's the basic gist of the idea. It's just saying that there's a sort of relationship going on between the beta 1 and the beta 2. So our goal is to perform a screening design using as few runs as possible, so small n design. And we're going to leverage those effect principles to do a two-stage analysis. And so in the first stage, we're going to focus on the fact that I think most of my model is going to be driven by my linear main effects. And the idea then is that, well, what I'm going to do is I'm going to fit a model with just my main effects. So I'm actually suggesting that we start with fitting what could be potentially the wrong model. I'm saying there could be some second order terms, but I'm actually just going to go into this and start by just fitting a model with these terms here. And the advantage of that is if I fit a model with just this first part here, there's only going to be 1 plus m effects there. And that is a regression problem that can be solved in the software. And this is just a simple regression model at this point, and you can just use simple t-tests for determining statistical significance of these linear main effects. And these are the equations that the software is doing. It takes this x1 transpose x1 inverse, x1 transpose y. And we also know what the variance is going to be for these estimates, which is important because this is what we need to be able to do statistical inference, to do testing. And the thing I want to point out is that there's two components that go into this. The first one, this sigma square piece, that is what was the variation that can't be explained by the model. And then we have this other piece, which I know completely without having collected any data because it just depends on the X matrix. So there's some ability for me to determine or figure out what this variance is without having collected any responses yet. And that's what makes this design problem feasible. And the stage 2 analysis is going to say, well, let me look at which factors are actually important in the stage 1 analysis, and then I'll consider all of the possible second order terms using the effect principles out of that. So the problem is now I want to figure out which design optimizes the statistical performance of both of these stages. Well, that's actually a really difficult problem. So let's focus on just the first stage to start out with. Now, I don't know how many of you do this and practice a lot or remember this, but there's actually this sort of equivalence between hypothesis testing with t-tests and also calculating confidence intervals and checking whether zero's in the interval or not. So that's actually an equivalent approach that I'm going to take is let's do inference for active effects by calculating these confidence intervals. But first I need to do some quick definitions. So one component of the confidence interval is going to be this thing that I call the design variance. It's the part of the variance that only depends on my design. Remember, we have these two pieces here, this sigma square piece that I have to estimate eventually. But then there's other piece here that just depends on my design. So I'll call those the design variances. It's just the diagonal elements of that matrix. But like I said, I still need to estimate variance. And if you go into your software and you tell it to fit just that main effect model, this is what it's going to do to calculate that estimate of variance. It's going to take this quadratic form. It's fine if you don't follow along the matrix notation. This is just the formula that it's going to use. And this denominator, which is really important, these are the degrees of freedom, the residual degrees of freedom for that model. It's just going to be n minus the rank of x1, which would just be m plus 1 in this case. So if I do this strategy, we would say that factor j is active, it's important in my screening experiment if the following confidence interval doesn't contain 0. So this is a confidence interval that you see all the time in basic statistics courses. You have your estimate, and then you add and subtract the same amount. You have this critical value from a t-distribution with this degrees of freedom, and then you have the standard error of your estimate that uses the square root of the variance estimate and then the square root of the design variance. All right, so let's talk about, remember, the point of the design is I want to find a design that has good statistical properties. What is a good statistical property of a confidence interval? Well, the reason why we like this approach with confidence intervals is the basic idea of a confidence interval is if you did repeated samples over and over again, sorry, my dog is starting to bark. If you did repeated samples and you calculated an interval over and over again, you would expect this percentage of the intervals to include the truth. And so this is what ensures our type 1 error rate of alpha, which assumes that we're talking about a beta j that's not important. But there's two things that we need for this to actually be met. The first one is that we need this estimate to be unbiased. And we also need the estimate of the variance to be unbiased as well. And I'm going to point out that that's not necessarily guaranteed. And so those are things that we need to make sure happen with the design that we pick. And so this is really talking about, again, for the inactive effects. But what about for the active effects? What we would like to have is to make sure that those intervals for the active effects are unlikely to contain 0. And so what we would like for those is for this piece, this part that we're adding and subtracting, called the margin of error, we would like that to be as small as possible. And that's going to be able to maximize our power for anything that's active. So what do we need for that, for this to be small? Well, all of these three pieces here, these are all positive numbers. So we want to make these shrunk as much as possible. So we would like for our degrees of freedom, this gx1, to be large, because what that will do is it drives this critical value here down, but it doesn't go arbitrarily close to 0. And in fact, the lower bound of it is what you would find for like the z critical value for a standard normal distribution. So there's a diminishing return that I'll point out and emphasize later on with how small to make this. And the other part of this is that you would like to minimize these design variances, these v1 to vm. So this is actually what traditional optimal designs do, is they just say, oh, you don't need to worry about sigma squared. All the experiments would have the same sigma squared value. Let's just focus on making these design variances as small as possible. But if you do this, this is actually implicitly assuming that you're doing an analysis where you don't need to estimate variance, which is absurd. That's always going to be a crucial part of what you're doing. And so that's something to keep in the back of our mind, is we need to make sure that the design we pick is going to be able to estimate our sigma squared and to estimate it unbiasedly. But let's go back to the design variances. Now, one thing that's known for these screening experiments with the way that I set it up, it's actually known that the lower bound for all these design variances is 1 over n. Therefore, we would like all of them to be 1 over n if possible. And this actually is possible in a lot of settings. It's achieved by what we call a strength 2 orthogonal array. The problem is that these types of designs only exist when the number of runs you have is a multiple of 4. So, 4, 8, 12, 16, so on and so forth. There's lots of scenarios where you might have an n in between those. And the last thing that you want to do is to say, well, I've got 17 runs, but I want n to be a multiple of 4. Well, let me just drop a run. That's the last thing you want to do. You want to be able to use as much resources as possible. So while this is possible to achieve if n's a multiple of 4, we want to make sure that we're doing the best we can and not sacrificing or removing any runs. Now, remember, one thing that I said is that for us to get that type 1 error rate that we want to make sure that we need to make sure that our estimates for our main effects are unbiased. The problem with that is I'm advocating the stage 1 analysis that you possibly are fitting the wrong model because you're not fitting any second order terms. Now, it's known that if you're doing that, then you might actually end up getting some bias. And that's going to be bad because bias is going to end up shifting your interval away from what the true value of beta is. And the amount of shifting is this expression here. It's a matrix expression um, involving the x1 and x2 matrices. So remember, this part here, I actually know what this is going in before I collect any data. The one thing I don't know is what this beta 2 value is. So one thing that's kind of cool about this that always really like blew my mind is that you can actually get rid of this aliasing, this bias term here completely if you're able to carefully pick a design where x1 and x2 are orthogonal to each other. And you can check that if you know what the x1 and x2 matrix are. So that's our goal is, can I also find a design where this alias matrix is 0, which is the same as saying these two pieces are orthogonal to each other. The other part that I said we need is I need an unbiased estimate of variance, and I'd also like a large number of degrees of freedom. We also have a consequence of fitting the wrong model, not just for bias of our linear main effects, but there's also bias that's going to happen with our variance term. And the problem with this is there's nothing we can do about that. That bias is always going to exist, and this is what that bias looks like. It's some ugly quadratic form component here. Again, that's a function of beta 2. And there's nothing I can do about x1 and x2 that makes this term go to 0. Any approach that I want to do anyway. And so what's going to end up happening is that if I estimate my variance using the traditional approach, it's going to give me a much larger estimate of variance. It's going to make my margins of error bigger. And what that's going to do is, while it will drive down my type 1 error rates, it's going to significantly decrease the power for the effects that are actually important. And that's what I really care about, is detecting active effects. So this is also not an ideal type of strategy. So let's start fixing things rather than talking about problems. In order for us to get an unbiased estimate of variance, it's actually not that difficult to be able to do that. All you need to do is to make sure that this largest possible model matrix here, X, which is both X1 and X2, you just need to make sure that that has some sort of rank deficiency, that its rank is less than n. So it might not be able to estimate all of your effects, but it's able to estimate other things. And so you can show that if that happens, then this quantity here, which is just replacing x1 with the full X matrix, this actually will be unbiased. And it'll be unbiased no matter what beta 2 is. And so it's a really simple fix. You just replace the gx1 and sigma x1 with gx and sigma x. That's going to give us our type 1 error rate of alpha. And then the goal there would be to just maximize this gx to make sure that the power is as large as possible. But there is a trade-off with that. So what are some techniques that I can use to make this gx large, or at least to make it bigger than 0? Well, there's two common approaches. One approach is to literally just take a run of your design matrix and then repeat it again. So we call that replication, and that leads to what we call pure error degrees of freedom. And so that would mean that in my total design, I have a subset of unique rows, and I have some rows that are repeated. So we could let just D1 to DU be my unique rows. And then for each of these, I can say how many times I replicate each one of them n sub I. And then that would make P our number of pure error degrees of freedom. So it's called pure error degrees of freedom because this is actually going to give us an estimate of variance that doesn't depend on our model being correctly specified. And so that's why it's an ideal way of estimating variance, but it's not the only way of estimating variance. If I really believe in that model, the second order model I wrote as being like, this is the largest possible model that I could possibly have, we might also have extra degrees of freedom called lack of fit degrees of freedom. That would come from potential other terms, like a cubic term or something like that, that we know actually is not really important. Now, this is going to be a model dependent estimator for sigma squared because it's really me banking on like a cubic term not being important. But for our purposes, that still works. That's still fine for us. So the point is that there's ways of dealing with this. but we're faced with a multi-objective optimization problem. There's all these things I want to try to accomplish at the same time. Just sort of like a summary here. We want to try to drive our design variances to the lower bound of 1 over n. I want to try to make my alias go to 0. I want to try to make this gx as large as possible. Obviously, I can't make it infinity, but I want to try to make it as big as possible. And so there's different strategies for this. The most common strategy that people use in practice that are taught in traditional design and experiment courses is to kind of do this one step at a time optimization, where they say, let's first minimize the design variances. And then among those designs that minimize the VJ, let's pick the one that has the smallest alias. Now, whenever you're doing multi-objective optimization, that's always dangerous to do sort of one at a time. You want to try to do a more balanced approach if possible. But I'm actually not going to take a balanced approach in this talk. I'm actually going to do the reverse of what this approach is saying. I'm going to say, let's first look at designs that I know guaranteed 0 aliasing. And then among those, let's find the ones that minimize the variances. And in fact, I'll show you that that's a better strategy and a faster strategy than this variance first approach. There's actually a very simple way for us to be able to get 0 aliasing, so guaranteed unbiasedness of the main effects, using this fold-over technique. And if you've ever heard of a fold-over, this is the most commonly cited reason for doing what we call a fold-over design, is that it guarantees 0 aliasing. And the idea is, I'll say what it is, but you'll see why it's called a fold-over. The idea is that you take half of the runs that you want, find that design, and then you take a mirror image of that design underneath it. And so you're kind of folding the design over onto itself. And so that means that all we need to do is find what I call a half design H, which has half the number of runs. And we just need to make sure that its rank is M, so that it's able to estimate all of our main effects. And then we can generate the full fold-over design, which I call D plus minus, by taking that original half design and then taking the negative of it. That's what allows us to, that's the sort of fold-over that's happening. And you can show that this guarantees that x1 transpose x2 is always going to be 0 if you use this technique. And the other nice thing about this is the design variances are completely determined by this H matrix here. So it's really a nice tractable math problem as well. In fact, many popular response surface designs employ this fold-over technique. If you've really been keeping up with the screening design literature lately, the two really popular types of classes of designs that gain a lot of interest are definitive screening designs, which take a fold over, or what they call a conference matrix. And then you have these OMARS designs, which are also sort of are using this fold over technique, but they don't have to have 3-level factors. But what I've discovered is that these fold over designs do more than just have 0 aliasing. These fold over designs also generate degrees of freedom for estimating variance, which is the part that most people have been ignoring, but is a crucial part of any analysis. You have to be able to estimate variance to do statistical inference. No one knows what the true sigma squared is. So here, let's talk about how that happens. So you start by partitioning the rows of your half design into capital G plus 1 groups. And that plus 1 is because you could potentially have what we call center runs. So if you have a numeric factor, you could have a 0 level. And if all of your factors are numeric, you could have a run of all zeros. So we call that a center run. That's a special case. But then all the other groups, you take the rows that are not 0, and you group them by whether they have replication or also if they have mirroring of each other. They're kind of equivalent. I'll give examples of what this means in just a minute. But I want to point out that under this grouping, I will allow for N0 to just be 0. Like there might not be any center runs. So let's just do a quick example with 4 factors and half designs of size 8. So the full design would be 16 runs. And so here are 3 possible half designs. This second half design here is the exact same as the first one. I just replaced the first row of all pluses with zeros. Oh, by the way, this plus and minus, this is just shorthand for +1 and -1. It just makes it nicer to present. And then I have this, these horizontal lines are talking about the grouping. So in these first two half designs, all of these groups are unique. They have just one run. But in this last half design here, this first run is in a group by itself. These runs are together. It's a replicate of the runs of all +1s. This third group is really showing what I mean by mirroring. It's got 3 runs in it. These first two are replicates of each other. And this last row is the same as these first two. It's just I flipped the signs. I've multiplied them by -1. So these would all be one group. So this is what I would call a mirror of these up there. And then these last two are mirrors of each other. So if you go through what I just described, the foldover of the half design has this grouping. So N0, there's no center run, so that's 0. But then all the N1 to N8, these are all ones. If I look at the second design, its half design is the same thing, except now I do have a center run, so that becomes 1. And then for the third design, no center runs, and then 1 replicate here, 2 in there, 3 in there, and 2 in there. That's where that comes from. And then the next column I have here, this is describing what the resulting pure error degrees of freedom are going to be for these 3 designs. This is going to have 0. This is going to have 1. And then this design is going to have 4 pure error degrees of freedom. Let's talk quickly about why this second design has 1 pure error degree of freedom. If I take this design right here and I flip the signs of everything, then this is going to create a unique row. That's going to create a unique row. All of these are actually ended up creating new rows if I multiply them by -1. The exception is the center run. If I multiply this row by -1, I'm going to get a row of all zeros again. So the complete foldover design that I generate, it's going to replicate 0, 0, 0, 0 2 times, which gives me 1 pure error degree of freedom. A similar thing happens with this design here. If I multiply these 2 rows by -1, not only will I replicate this row twice, but I'm also going to replicate the row of all -1s twice as well. And so that's going to give me more pure error degrees of freedom than what I had originally, which is why that's 4. This second column here, this lack of fit, there's no real way of visualizing this. This is just what the total number is for the lack of fit. And what I really care about is this g of x. Now, I also want to point out, I have this for 2 different models. This is for the model without quadratic effects, so just the 2-factor interactions. And this is the model if I also include quadratic effects. So sometimes this Lx will change depending on what that second order model is. You'll see here Lx dropped by 1 degree of freedom when I started to include quadratic effects. So that can be model dependent. But the point is that all of this is actually tractable. I worked out all the formulas for this. And so here's the foldover theorem that I came up with. If you have a half design with m plus v more runs that form these groups, then the foldover design has these following 4 properties. Aliasing is going to be 0. That's already a well-known result. I didn't prove that. But your total degrees of freedom, gx, is going to be bounded below by v, the number of runs you're adding to it. So that tells me I'll know at least a lower bound for what the degrees of freedom would be. And the lack of fit degrees of freedom is going to have this lower bound. We don't need to worry about the formulas. And then the pure error degrees of freedom is going to have these 2 pieces added together. This first one here is just to take into account whether you have center runs. If there aren't any center runs, this part goes away. And then you have this component right here. So as I said, I'm really not the first one to kind of come up with this, but I am the first one to sort of generalize it for any sort of situation. Brad Jones and Chris Knoxtime in 2017, they discovered these definitive screen designs. Their half designs were what they called conference matrices with m plus 2 runs. And so using my formula, they take a foldover of that would generate at least 2 degrees of freedom. And in fact, the way they do this, it generates exactly 2 degrees of freedom and the 2 lack of fit degrees of freedom. All right, so for what we're trying to do, we're going to say, what's the best foldover design for stage 1 inference? And the nice things about this is that I automatically know I get zero aliasing out of it. I know I get unbiased estimation of the variance. So really this comes down to just trying to maximize degrees of freedom for estimating variance and also minimizing design variances. And so the way I'm going to rank designs is by minimizing what I call the average expected margin of error. So the idea is that this would make my intervals in some overall sense as small as possible and always centered at the true value. And so this is kind of an average of the expected margin of error. And then I did the math and showed that this is proportional to the multiplication of these three pieces. You've got the t critical value. This is always going to go down as you increase gx, but again, it has that lower bound of the z critical value. You have this annoying constant term, which has this expression here. Again, not terribly important, but it's there. And then you have the average of the square root of the design variances. It actually has a really nice interpretation. It doesn't look like it by looking at these formulas, but it has a really nice interpretation in that the average expected margin of error is telling you the smallest signal to noise ratio you have that would achieve a power of at least 1 minus alpha. And this is commonly talked about with power analyses, like what's the minimum signal to noise ratio you want to be able to detect. And so this actually does have a connection to power, which is another reason why I call this powerful foldover designs. And I'll talk about more of how that can be used in practice. But as I was saying in our chat before my talk started, I'm really big into making sure you pick a criterion that makes sense, but a criterion is only good if you actually know how to find the optimal design under that criterion. And so what I'm going to propose doing is just a very simple search algorithm that I've coded up in R, and I'll demonstrate a little in a little bit. But the beauty of this is I don't need to find an optimal end run design because I'm planning on doing a foldover. I only need to find an optimal half run design. So I've automatically cut the complexity of the computations in half by doing this. And so I want to find an optimal half design that minimizes this average expected margin of error. And to do this, you have to set what you want your alpha level to be. And so this can be driven by what you want your power to be. I usually pick 0.05, talking about power of like 0.95. You can set a minimum number of center runs that you want. It can add more if it decides it needs more, but you can set a minimum number that you want. It can also set a minimum number of replication that you want in your half design as well. And again, the algorithm might find it needs more replicates if it improves it, but it doesn't necessarily have to. I also allow people to be able to specify a mix of categorical and numeric factors. I do recommend that if you have a numeric factor and you care about quadratic effects, that you require a zero level in the half design to be able to just be able to estimate quadratic effects. And my algorithm does do that automatically. So let's go back to the ethylene experiment and demonstrate that. So that, remember, that had 20 runs. And so here's actually the full 20 run experiment. I'm not showing the half design here, but you can tell I'm doing a foldover because I've arranged my runs. I've kind of written it in terms of the transpose. So now this column is a run because I can't fit it on a slide. But you can see this column is a mirror image of this column here. So I've folded these over and I've grouped these by different pairs. But you can see in here, I've got some replication going on. And you can show that this design is going to have 3 total degrees of freedom for estimating variance. It's got 2 pure error degrees of freedom and 1 lack of fit degree of freedom. And this equation I have right here, if you were to do a traditional screening experiment, you would pick one that a 20 is a multiple of 4, so you can have a 1 over n for all of your design variances. So this right here would be the lower bound if we were to pick that type of design. You can see the design I'm doing has a bigger number, which seems like a bad idea. The problem is that if I were to run a design with this value, it would not be able to estimate variance. So there are some limitations with the actual analysis of that. And the average expected margin of error for this experiment up here is 0.791. So anything with a signal to noise ratio of 0.791 or higher, I would have a power of at least 0.95 to detect it. And so I did an analysis on this experiment. We ended up finding out that only these three factors were important. So that's kind of this effect factor sparsity coming into play. Only 3 of the 8 were actually important. This is my estimate of variance. Then I can do effect heredity and say, well, the only second order effects that I would consider are all two-factor interactions among these 3. And there's only 3 of those, D1, D2, D1, D4, and D2, D4. And I use this, what I call modified BIC criterion. I'm not going to go into what that is, to try to figure out whether I should add any of these second order terms. We want to minimize MBIC, and we concluded that adding D1, D4 two-factor interaction gives us a slightly better model. It fit the data pretty well, and we were all very, very happy. So this was a very successful experiment in what seemed like something overwhelming with so many possible runs. You can see these effect principles in action. Now, I do want to go back, with the time that I have left, I do want to go back to talking about what I was saying with making g of x as large as possible and how there is a diminishing return with that. So g of x actually comes into play in 2 pieces. Let me go back to point it out. So g of x affects these 2 components here. And the point is that making gx large, how much is it going to decrease these quantities by? Well, it's going to start to taper off at some point. And here we see this in action for different levels of alpha. If alpha is 0.05, for example, the value that we commonly use in practice, you can see going from like 1 to 2, you see a sharp decrease from a little over 10 to 4. But then when I go to 3, well, it's still dropping by about 4 to 3. But as I start to add more, I'm really only decreasing this by a marginal amount. So this rule of just arbitrarily making gx large, it's not a good idea. And that's a benefit of that, evaluating it in terms of this actual number rather than just the gx number itself. And this is what's actually coming into play in the actual analysis. And so I usually recommend having 3 or 4 for g of x. That's usually sufficient based off of looking at this. You're not really going to get much extra benefit. And my criterion would take that into account. But I bring this up because I've been talking about how great foldover designs are, but there's a downside to this foldover theorem because it basically says that you don't want to fold over large designs. So for example, if I had 40 runs and 8 factors, so like twice as much as that ethylene experiment, if I were to do the fold over approach without thinking about it, then my half design would have 20 runs. And so that 8 plus 12 would be my formula. This is that V term. That means that my G of X would be at least 12. I can't make it any smaller than that. And that's much larger than what I'm recommending that you do. And so the reason why this is bad is because increasing G of X larger than it needs to be comes at the cost of our ability to do that second stage screening, estimating interaction effects and quadratic effects. So we're not really gaining a whole lot by doing a G of X that's this large. And then when I first realized this, I thought, well, man, maybe foldover designs aren't that great. But then I realized there's actually a really nice strategy that we can do to fix this problem. And the idea is that you choose a minimum signal to noise ratio that you would want to be able to detect for your main effects. And then you construct a foldover design using as few runs as possible so that you have an average expected margin of error that is less than that value. So it gives you the power that you want to be able to detect those active effects. Then if you have more runs that you can add, you can augment that foldover design with more runs to really target on your inference for the second order effects. And this is kind of getting a little beyond, but there's the criterion called a Bayesian A criterion that allows you to do this. And the nice thing about this is that you could determine these augmented runs before you collect your data, but you could also determine these augmented runs after you collect data. So you could really do this in a sequential approach if you wanted to really maximize the potential of your design. So let me end this with a really quick demonstration. What I'm going to do is I'm going to pick a very common classical design problem and show you what people recommend you do is actually a bad idea or can be a bad idea. So let's do 16 runs. That's a multiple of 4. So that special orthogonal array I talked about exists, and then 5 factors. Let's ignore quadratic effects. Let's just say I have a possible 2-factor interaction model. What's interesting about this is that if I do 16 runs, I actually can estimate all of my effects if I wanted to. I won't have any degrees of freedom for estimating variance though, but there is a common technique to deal with that. So if you presented this problem in a classic design class, the go-to answer would be, oh, let's do a half fractional factorial design. It has a lot of nice things. It not only can it estimate all of your main effects and interaction parameters, but it estimates all of them with the smallest possible variance. So how can you beat that? Well, like I said, you can't estimate sigma squared, so you have to do this other graphical method called the length method that generates an estimate of sigma squared, assuming this effect principle approach. And the point is that there's situations where this method can explode and totally point you to the wrong conclusions if these principles don't hold. And so I generated 3 competing foldover designs with this augmented approach where I do 14 runs and then I add 2 more runs with the Bayesian A criterion. And so here are the 3 designs that I generated. I'm not going to go into the structure of all these things. Let's just jump to the average expected margin of error. So this design I'm calling C3, it has a large average expected margin of error. So it's not going to be quite as powerful as these other 2 designs. And in fact, this middle design would be the best in terms of power for our main effects. And you can see that it gets a lot of its power from having 4 pure error degrees of freedom. This design here has 3 degrees of freedom, combining 1 lack of fit and 2 pure error. And this design here just has 2 lack of fit degrees of freedom. So I did a simulation study here where I simulated 500 responses and I manipulated different things. I manipulated the number of active main effects and the number of active 2-factor interactions. I generated effects so that they did have a desired signal-to-noise ratio. And I analyzed all of my 3 designs using my augmented 2-stage analysis. When I analyzed the competing half fractional factorial design, I used the length method. And I reported the true positive rate and the false positive rate across the main effects and the 2-factor interactions. So here are the 3 scenarios that I looked at. This first number describes how many active main effects I have. So these last 2 scenarios, they're saying all 5 factors are important. So I would need to get all 5 of them to be happy. And then the second number over here, this is the number of active interaction effects. And then the number in parentheses is the signal to noise ratio. So the larger the signal to noise ratio is, the easier it should be to detect effects. So here I'm kind of describing what the issues might be for some of these scenarios. Scenarios 1 and 3, everything should work beautifully. I don't have very many active effects, large signal to noise ratios. 2 and 4 are the exact same thing, but I made the signal to noise ratio smaller. So that's going to be a little bit more difficult with the effect principles. And the last 2 scenarios, I'm expecting traditional methods to just blow up because I have a lot of active effects and it's going to be difficult for me to figure out what's important and what isn't. So here are my plots of the true positive rate and the false positive rate. The black line is the C3 design. The green line is the one I said that had the best average expected margin of error. The red line was the one that was a little bit worse than that in terms of our criterion. But really, the blue line is what we should focus on. This is the classical approach. And you can see in these last 2 scenarios that I said that the effect principles do not hold, it does a terrible job. It basically cannot detect anything as being active. It says everything is actually inactive. And so this is a worst case scenario. You would never want to see a design that has this type of property. And the point is that you can see that my designs that I came up with, these foldover designs, even in the optimal scenarios for the fractional factorial design, my designs are still highly competitive. And in fact, sometimes beating the traditional design in terms of the main effects, although maybe with a slightly higher false positive rate, which is totally acceptable in this type of situation. For the 2-factor interactions, you can see all the methods kind of struggle a little bit, but again, our method is still just as competitive as the other methods. Again, fractional factorial designs, they just struggle when there might be a lot of active effects. So just to quickly summarize, hopefully I've gotten you interested in fold-over designs. If you already knew about fold-over designs, hopefully I've enlightened you about this brand new property, about how they generate degrees of freedom for variance. I talked about this two-stage analysis and how fold-over designs really promote the statistical properties of that analysis. I talked about or mentioned that there was this construction algorithm that you can run. I'll demo that in just a second. And I also talked about this augmented design that you should use if you have a large number of runs available to you, and you want to kind of do a smaller fold-over design to start out with. So before I go to questions, let me just demo this construction algorithm. So I have this function library script that has all the important functions that you need. So you need to run that first. Actually, let me make sure I'm running the whole thing. So once you have this run, it has all the functions that you need. And so in this R code, you need to specify the number of factors, the number of runs that you have. You need to specify whether you have quadratic effects, the number of initial designs you want to do. This is the number of required replications that you want of non-center runs. This is the number of center runs you want, alpha value. I'll just move on. There's a lot of extra things to talk about this, but the point is that you can run all these things. And so what I have set up here is my construction algorithm for the toy example that we just looked at with 5 factors and 16 runs. So I start out with 14 runs and then I'll augment it. So let me just show you how quickly this can work. And the beauty of this is that, yes, my final fold-over design will have 14 runs, but I only need to find a design with 7 runs when I'm doing my construction algorithm. And so I'll click run. And so what this is showing you, this output, it shows you the first initial design average margin of error, and then the bottom number is the final average margin of error. And you can see that in almost all cases, we end up converging to a design with the exact same value at the end. Now, this actually isn't the average margin of error. This is the value without dividing by m. So this is me dividing that by m, and the average margin of error is 0.7767. And so that's that signal-to-noise ratio that we would want. Then this function actually takes the fold-over design. It gives you a table describing that N0, N1, so on and so forth grouping. So we can see that it ended up replicating this run twice, and then this run, whatever that is, twice as well. This is where we get our 4 pure error degrees of freedom. And this is just demonstrating what that design looks like. So this is the full fold-over design, not the half design. This function here actually will show me what the individual design standard errors are, and it'll verify that I have 0 aliasing. I can see zeros everywhere. I won't run this for sake of time. And then if I want to augment it with 2 more runs, I specify how many runs I want to augment it with. And then this runs the augmentation algorithm. And this one is super fast because it's only considering 2 extra runs. And it's done. That was almost instantaneous. These are what the 2 extra runs it's recommending. And then if I R-bind or attach all this, this would be my final complete design. And the one thing to keep in mind is that when you do your analysis, you want to do your stage 1 analysis just using the first 14 runs. You don't want to use the last 2 runs. And so after you do the first 14 runs, then you can use all of the data, all of the runs to do your second stage screening. Okay, I will wrap up there. How do I? Sorry, let me stop my screen share. Did I stop screen sharing?
Yes.
Okay, great. I thought I messed that up. Fantastic. All right. Well, thank you very much. I can take any questions you might have. I think you're muted.
Well, I guess I just have to say, it's like, wow, you can eke even more out of a fold-over design.
Yeah, it was there the entire time. And I'm just shocked that no one has really appreciated it. So Brad and Chris, the guys who came up with definitive screen designs, uh, they stumbled upon this um, because they did this fake factor approach where they said that um, you could take a larger conference matrix and fold that over. And so they called it like fake factor degrees of freedom. But then, with my linear algebra brain, I realized, well, like you don't have to do this with like a fake factor approach. You just need your matrix, your half design to be like rank deficient.
Hmm.
And anytime you fold it over, it's going to work. You're going to get extra degrees of freedom. And um, in their paper, they talked about this sort of two-stage analysis. And so full credit to them about that idea. And yeah, I just realized that, their technique could be generalized to all sorts of different cases. And I've really been doing a strong push for people in design to appreciate that variance estimation is always an important part of your analysis, and that it should be treated just as important as being able to estimate your regression coefficients, if not more important. Because if you get that number wrong, then pretty much everything else is going to crumble, uh, in
Mhm.
my experience.
Right, right. Jonathan, I have a couple of questions. What criteria do you recommend to select the amount of runs and the amount of factors, in the experiment?
Yeah.
Because that's something that we always struggle right at the beginning. So what do you recommend?
I'll make the question even harder for you. Not only that,
Okay.
but how do you choose the settings for these numeric factors, right? How wide do you
Right,
go?
right.
Um,
Exactly.
so yeah, I'm just acknowledging that the problem's even harder than that.
Mhm.
Yeah,
I don't
that's
understand. I don't
where.
understand why you call that a problem. I mean, I guess maybe it's the way I'm conceptualizing, why we do
Mhm,
screening studies. And the number one to me is, well, if the levels are too close, you don't see anything. And if they're too far
mhm,
apart, you might go to you don't really see anything either. So, I mean, that just comes with the territory. It's like if we knew, we wouldn't
right,
be running experiments. I mean, so I was just like,
right,
oh, okay, whatever. You got it. You throw something out there where you think the size of the effect or the size of the difference that should produce a noticeable difference in effect, and maybe it doesn't, but I guess that's part of the fun. Again, that's the way I look at it, because
right.
if I knew it,
Well,
I wouldn't be running experiments.
right, yeah. No, but like that's a great mindset to have, but you have these poor grad students that are terrified of breaking something, and uh they're worried about going too extreme, and possibly getting no response out of it at all if they go too far. But you're right, if they're too conservative, you'll say like, well, there's nothing there, when in fact that's not totally accurate. It's like, well, there's nothing there if you only look in this narrow range.
Yeah,
So
yeah.
yeah, that's just an interesting um question that's come up with a lot of my consulting experiences that I have. But to answer the original question, which is not easy to answer, um, really, I think it comes down to what a lot of statisticians hate, which is the power analysis, like knowing what you can reliably expect to get out of the experiment to be able to actually um, to detect. And the nice thing about it is, if you can frame it as signal to noise ratio, you don't really need to know exact numbers, because it's all relative to whatever the noise might be. Um, but it's still something that uh, I don't know, not everyone agrees on. You know, to be able to detect really small signal to noise ratios, you have to have a lot of runs. And the only way to get around that is to make sure that whatever process is that you're looking at, that you have it as controlled as possible, so that sigma term is small. So like local error control techniques like blocking or any other factors that you think might be important. That's really all you can do. And if we're talking about the framework that I'm proposing here, you want to make sure that it's not just N or M separately, it's about them together. And I think like one rule of thumb is you would hope to be able to detect half, like hopefully there are no more than half of the number of runs you have as the effects that are actually important. And that was actually the last scenario that I talked about in my simulation. I had 10 total effects that were important out of 16. So I was really pushing that. But the surprising thing is my methods still were okay.
Right.
In those methods. Still not great though. No one's gonna be happy about a true positive rate of 50%. Like I can detect 50 things that are actually important. Well, that's not what I want to hear. I want to hear that you can actually do like 90% or higher than that if you want to. But I mean, really, I think like doing simulation studies, if you can, is a good
Okay.
idea.
Okay.
So, but yeah, that's
Yeah.
a
Yeah.
complicated question. And you'll notice that
Yeah. Yeah.
that topic is mostly totally avoided in design textbooks just because it's so nuanced.
Yeah.
And yeah, I saw a question in the chat.
Yeah, and I was asking that question because when I was working in the area of medical devices and trying to conduct complicated validations, then conducted the analysis and then come back with the plant managers or manufacturing guys, right? And they said, we need to do all that, all those runs. And you see what I mean?
Yeah.
Right? It's
Yeah.
gonna cost a lot of money, man. Okay.
Mhm.
Says, well, we need to have an argument in our hands in order to convince these guys, well, you want to do it or not, because we can conduct it, but you're not gonna get anything,
Mhm.
any benefit at all. Okay. So
Yeah.
if you really wanna get a good benefit, we need to do this. Okay.
Mhm.
You don't have any other choice. So that's the thing.
Right. Well, how much is it going to cost you to send out an inferior product, right? Like it's very short-sighted to.
Exactly. Yeah.
Well, I
And
mean,
my other
you have to give them some grace on the fact that, they don't necessarily, not everybody like thinks in like total systems and potential, like they don't even understand the Pareto principle at all,
Mhm.
or they have real simplistic models for how things work. And, so I think you almost have to approach what I like about this is, okay, so if you can tell them, hey, we're screening because there's things that literally don't have an effect, or their effect is well, it's not significant, but we're not testing things that we don't think are significant. We're testing things that we are significant, but we're not sure which one is truly significant, because so much stuff
Mhm.
has just come out of, old wise tales, accidents, and all this other
Mhm.
stuff. And it's not profound knowledge, right? It's like,
Right.
yeah, well, this, when I twisted this knob that time, the problem went away. And it's like,
Mhm.
but was it that knob or did something else change, at the same time? And so that's the part where, I love screening experiments for that fact is, okay, well, let's get in here quick and try to maximize the learning. And I think this is very interesting how you're approaching it. It's like, oh, okay. I mean, it's way more sophisticated than anything I've ever tried, but it's like,
Mhm.
oh, okay, you can get a little more juice out of this, with the squeeze. And
Mhm.
it's like, oh, okay. So, that's for people, of course, plant managers aren't going to have that level of, how should I say, detail, and they shouldn't, right? They're managers. It's for us as
Right.
experts to go in there and say, oh, you know what, I can do something for you that'll produce a more reliable result or a more informative result. I mean, that's I think the argument I would make for using this kind of thing. It's like, oh, you know what? You can goose it a little bit, and
Hmm.
maybe it's a little more
Well,
efficient, and maybe it's a little more reliable, right?
exactly, exactly.
Yeah, I
You know,
I
in my
became I became an expert when I was at Virginia Tech. I got my stipend by consulting and collaboration, and
Mhm.
so I learned very quickly that um, the most important thing in that first meeting is understanding what the other person understood when it came to statistics and knowing the
right.
best way to sell it to them so they would understand it, right? Like I knew it was important, but how do I sell it to them?
Right.
I wanted to get to so Hector has a number of questions in the chat. I wanted to make sure that
Oh,
I
okay.
got to those. Um, so the first one he asked was, do you need any replication to confirm? Do you mean for that ethylene experiment? Yeah, okay. Um, what's funny about that is so Kyle, the graduate student on there, he said, hey, our funding's been pulled. Tell me what runs you need me to run before we lose the equipment. And so remember, we did have replication in there, so there's kind of some replication that went on in there. But the thing is that he went into this assuming that he just wanted to look at the extreme points, the plus ones and the minus ones, even though these were numeric settings. And so what I told him is that, well, it looks like this model works pretty well at the corner points and the extreme points. Let's try to see what happens with, what's going on with the center runs and see if there might be any quadratic effects. So I got him to augment his design using actually a conference matrix. So like it's a matrix of plus and minus ones, but it's zeros along the diagonal to see if there were any quadratic effects. And he actually had his defense 2 weeks ago or something, and I realized like, oh no, I never analyzed the data with those extra runs, so I'm doing it like while he's doing his defense, and I actually found out that two-factor interaction that I found was not statistically significant when I added more. In fact, it wasn't statistically significant in the original data. It had an alpha of like 0.15. It was just that BIC criterion made it slightly smaller, but his sixth factor actually had a significant quadratic effect, which was pretty surprising given that it wasn't very well powered to be able to detect something like that. So it had a very strong quadratic effect. So that there's even more steps that need to come with this than what I originally uh, presented on that. So that was a great question. So how can you be sure that interactions are important? Was that in reference to the ethylene experiment, or was that just sort of like in general? Sorry, you're muted.
Oh,
Design of experiment.
Oh, okay. Well, I mean, just like with main effects, you can test for those interactions. Uh, but I mean, that's really the only way I think I can answer that. I don't really know. That's the best answer that I could think of for how you can be sure interactions are important is just I mean, the way that it's like this, it's a specific type of interaction. It is like that special type of bilinear interaction. And I guess those also can be a better, helpful way to understand those is by doing like an interaction plot where you
Mm-hmm.
look at the effect of one factor with the other factor fixed. So it's kind of helpful to kind of pair those two things together, because just because something is statistically significant doesn't mean that it's actually like causing a huge effect uh, in the data itself.
right,
But
right,
sometimes the factors that are important, we look at interactions of those factors and see if they are uh, causing effect,
Hmm.
greater effect or not.
Right. And the whole point of foldover designs is that if you don't account for the aliasing that can happen if you just fit a main effect model, it doesn't take a very strong interaction to completely screw up your inference for your main effects, it can kind of propagate that bias and just totally change your conclusions. And I see that happen a lot. And I've actually come to appreciate
Right.
that. I think I've heard that George Box felt the same way, that if you're going to
Mm,
minimize any one of those two, aliasing actually should be the more important thing to
okay.
worry about.
Are you talking about the Box? You know, the statistician?
Yes, George Box. Yep.
Oh, George Box,
Kind of
yeah.
the,
He
yep.
he passed away, right? Like 2 years ago, something like that.
That was a while. It was just before
Oh,
COVID, I think.
oh,
Mm,
before COVID. Okay, I
Yeah.
see.
If you want a recommendation, his autobiography, The Accidental Statistician, is really interesting uh, to
Okay,
read. He was a great writer. So it's
okay,
kind of cool
yeah.
to hear his insights. And then the last question Hector asked is, are orthogonal designs always desired? I think the point of my talk was no.
okay.
Yeah,
That
I use his ideas about the EPC, the engineering process control, using
mhm.
stochastic processes from him from Vance.
Yeah. No,
Yeah, he was
he
great.
was very influential. Yeah, he always
Yeah.
had the practitioner in mind. I think that's why he was so successful, because he wasn't a statistician by training. He was a chemical engineer, and
Okay.
he knew how people wanted to think about
Wow.
problems and did what he could to help people um, with that.
Yeah.
So yeah, I never got to meet him, but he's a very impressive man.
Very, very impressive.
But
Yeah.
but yeah,
So,
Hector, about what you said about are orthogonal designs always desired, I think you don't like it's just a coincidence that orthogonality tends to lead to nice statistical properties, but you don't want to assume that that is always the case. If you've ever learned about these orthogonal these Omar's designs that have come out with Peter Host and his group, um, a lot of them are great, but it's actually really easy to create orthogonality between things if you allow zero levels, right? A vector of all zeros is orthogonal to everything.
Right.
wow.
So it's orthogonality is not the end all be all.
All
There's
right.
different ways to achieve orthogonality. So just something to be aware of. And that's the nice thing about my criterion is it says I'm not trying to find a specific design structure. I'm just trying to find whatever design is out there that makes these things that are actually going to show up in your analysis as small as possible.
Right.
Thank you, John.
Well,
Welcome.
Jonathan, the math that you presented for the fold over designs is beautiful. Really, I like it a lot. Yeah,
Thank you.
it's really excellent. You know what you presented.
And
My
that
question is in reference to the fold over design technique. Uh, which software is using this technique actually?
uh let's see. So Jump does allow you to do foldovers.
Okay,
Um
okay,
I gave this talk at Jump because they're just
okay.
down the road from me,
All right.
and I know the people that work there pretty well, and I was actually able to a lot of extra clicking, but I was able
Okay.
to get their software to do the algorithm that
I
I
see.
talked
Okay.
about.
Excellent.
So
All right.
they have that functionality, and I don't know if they're planning on implementing it at all. I mean, I talked to their developers, and I'm like, you guys already have all these things built in here. You just need to like wrap them all together. So it's possible that they'll release that in a future version of Jump. I'm not sure. Um, I think Jump is really the design software I had the most familiarity with.
Mm,
FX, which is the new software from the people that came up with Omar's designs, they will they've enumerated a lot of designs, and many of them are foldover designs, but they don't quite construct things the way that I do it.
I see.
But I
Okay.
mean, really, the beauty of the foldover designs is it's not hard at all to do it yourself. You know, you just take this original matrix and you just multiply it by -1. You just flip the signs for a lot of things, and there it is. And you don't have to worry about checking it. It's guaranteed to have zero aliasing.
Well, for sure, I'm gonna have to review the recording, you know, because that must be beautiful. Really, I need to understand it very well.
Yeah, this talk is definitely a more academic talk. So apologies for that.
No,
I
it's
think
great. It's great. Great. I
yeah,
like it.
it's, you know, when you're into the research, everything looks so easy. And it's been a couple months since I've given this talk, and I'm like, oh wow, like this is definitely a lot of equations. Hopefully, I was trying to point out, like, you've seen this before, this confidence interval expression. It's got all the ingredients that we're used to seeing, maybe with different notation. But
Right.
in my paper, I talked about the foldover theorem, which seems like super scary for people that aren't used to doing theorems and proofs like that. But in the paper, the way I read it, I actually give a very intuitive explanation for why these numbers come up. With just that those three designs, those examples, I kind of give it an intuition about, like, this is why these are the equations that show up. And then if you really want to nerd out with the linear algebra, you can go to the supplementary materials and see how it works out in terms of that. But you don't need that to really convince yourself that it works out.
See.
Thank you very much, John.
You're welcome.
Excellent present. I told you guys, you know, this is high level statistics, and this is the best statisticians in the country. Okay.
Well,
And
I'm on
I'm
the
not
shoulders of giants.
I'm not overselling anything, okay, Jonathan? No.
Okay, thank you.
It's true.
Thank you, Jonathan.
Yeah, thanks
You're
a lot.
welcome.
This was interesting. I guess it was quite illuminating that there's, as you said, it's a little surprising to me that there's more to get out of this, you know.
Yeah, it just I don't mind telling it came to me when I was in the Trader Joe's parking lot. I was just driving home from work and I stopped at Trader Joe's, and I just I was like, oh my God, like, so
Oh man.
it was really cool when that
Wow.
just popped up. So
Cool. All right. Well, thanks a lot, John. Really appreciate the time and the sharing your insights. So,
you're welcome. If y'all have any questions about the paper or anything like that, feel free to email me. You know, I want people to start using these things because I think they are really practical. And
Yes.
I'm hoping that people start gravitating towards these and away from the classical designs.
Absolutely. Yeah.
Thank you very much.
Thank you very much.
You're welcome.
All
Thank you very
right,
much for
guys.
having me.
Thank you.
I hope to
Excellent.
Thank
have a
you.
good night.
Bye.
good night.
Bye.
All right. See you guys.
All right, Keith. Good questions.